Compare two patients. One has high body mass but safely stores fat subcutaneously. The other has lower mass but dense fat infiltrating the visceral cavity. BMI flags the first as high risk, completely overlooking the second, unable to distinguish safe storage from toxic infiltration. To understand why the thinner patient faces greater metabolic risk, we must examine the adipose tissue expandability hypothesis. Subcutaneous adipose tissue acts as the body's primary reservoir for storing excess energy, but its capacity for expansion is strictly finite. When this storage threshold is breached, excess triglycerides are forcibly redirected, spilling over into the visceral cavity and non-adipose tissues. This process of ectopic fat deposition causes lipids to accumulate, such as the liver, the heart, and the pancreas. Over time, this creeping lipid infiltration physically encases and deeply penetrates the functional anatomy of these essential living organs. Inside a normal adipocyte, a triglyceride is biologically inert. Inside a regular organ cell, that same lipid becomes mechanically and chemically toxic. Systemic metabolic disease represents a critical failure of fat distribution, overriding total body mass as the primary trigger for toxic physiological cascades. The liver is the central axis of ectopic spillover, receiving 60% of free fatty acids directly from visceral fat. The critical tipping point occurs when hepatic fatty acid uptake exceeds beta-oxidation capacity. Triglycerides then accumulate inside hepatocytes, driving steatotic liver disease. This spillover follows a parallel path to the pancreas. Here, functional acinar cells undergo apoptosis and are physically replaced by invasive fat cells. As fat replaces functional tissue, beta cells fail. This directly impairs insulin secretion and elevates the risk of pancreatic adenocarcinoma. The cardiovascular system experiences a similar invasion, with lipids depositing into the epicardium surrounding the heart and directly into the myocardium itself. Once established, epicardial fat acts as an active paracrine organ. It secretes pro-inflammatory cytokines directly into the heart muscle and coronary arteries, accelerating atherosclerosis and diastolic dysfunction. We also see lipid accumulation within skeletal muscle fibers, known as myosteatosis. But because endurance athletes often possess high intramyocellular lipids alongside high insulin sensitivity, it appears the metabolic turnover of lipids, rather than their mere presence, determines their toxicity. Ectopic fat is an interconnected map of multi-organ metabolic failure, all driven by the initial visceral spillover. Isolating the dietary inputs forcing this cellular overflow reveals the specific role of fructose as a metabolic catalyst. While glucose can be utilized by nearly every cell in the human body, fructose is metabolized almost exclusively in the liver. Tracking the biochemical pathway, the liver rapidly converts fructose into citrate. The enzyme ATP citrate lyase then converts it into acetyl-CoA, initiating de novo lipogenesis. This lipogenic process bypasses metabolic bottlenecks, manufacturing triglycerides regardless of energy needs, leading to unchecked cellular lipid accumulation. Ultra-processed foods exacerbate this lipid dysregulation through high energy density and nutrient scarcity. These formulations guarantee a rapid positive energy balance, which directly accelerates the hypertrophy of existing adipose tissue. Furthermore, industrial additives and trans fats in these foods induce systemic low-grade inflammation. This impairs normal pre-adipocyte differentiation in subcutaneous fat, effectively forcing new lipids to seek ectopic sites. Refined fructose and ultra-processed foods act as biochemical saboteurs, actively forcing the liver into a state of pathological lipid overproduction. Zooming past the organ level and pushing through the membrane of a non-adipose cell allows us to observe lipotoxicity at the molecular scale. As free fatty acids penetrate the cell, transport proteins convert them into long-chain acyl-CoA molecules. The physiological breaking point occurs when mitochondrial beta-oxidation is insufficient to clear this sudden influx. When the primary clearance pathway backs up, uncleared molecules are shunted towards synthesizing highly reactive, toxic metabolites, diacylglycerols and ceramides. These newly formed metabolites act as rogue signaling molecules. They activate destructive serine and threonine kinases that physically attach to and block incoming insulin receptor substrates. This specific kinase blockade breaks the insulin signaling cascade, creating the mechanical root cause of cellular insulin resistance. Systemic insulin resistance is the direct result of toxic lipid byproducts physically jamming cellular communication networks. This lipid overload eventually breaks the cell's major manufacturing hubs, beginning with the endoplasmic reticulum. As lipotoxicity perturbs the ER membrane and overwhelms its protein folding capacity, the organelle triggers an emergency protocol called the unfolded protein response. This model shows the three distinct sensor nodes of that response: PERK, IRE1-alpha, and ATF6-alpha. When ER stress is persistent, the prolonged activation of these sensors ultimately triggers cellular apoptosis. This structural stress also severs the critical communication lines between the ER and the mitochondria, severely impairing mitochondrial respiration and lowering the spare respiratory capacity of the cell. Failing mitochondria increase the production of reactive oxygen species, generating electrophilic lipid enols that directly damage and covalently modify cellular DNA, a driver of genomic instability. This oxidative DNA damage forces the cell to initiate its own senescence program. The cell permanently halts its cycle, transforming into a rigid, dysfunctional state. These senescent cells exhibit a secretory phenotype, sonically leaking inflammatory cytokines that spread cellular stress and contribute to stem cell exhaustion in tissues like the bone marrow. Through the combined impact of genomic instability, mitochondrial failure, and the spread of inflammatory senescence, ectopic fat drives the primary hallmarks of biological decay across multiple organ systems. Given the scale of this cellular damage, clinical medicine requires tools to track this infiltration before it reaches the threshold of organ failure. Standard lipid panels, which measure circulating triglycerides and LDL, are blind to regional ectopic deposition inside the organs. Bypassing standard metrics to track precision biomarkers like FGF21 and GDF15 allows for a more accurate assessment of internal metabolic stress. FGF21 signals metabolic stress in the liver and muscle, while GDF15 exposes mitochondrial hepatopathies. Spikes provide an early warning of subclinical organ stress. Integrating these precision diagnostics allows for an accurate assessment of a patient's metabolic state, regardless of their BMI. Despite the severity of the cellular damage, ectopic lipid depots are highly dynamic and can be reversed through targeted interventions. This chart compares dietary interventions. A very low-energy ketogenic diet achieves a 77% reduction in hepatic steatosis, rapidly clearing intrahepatic triglycerides over 12 weeks. Whole food plant-based diets offer a different pathway, using high fiber to counteract de novo lipogenesis and improve postprandial insulin sensitivity. By cutting lipogenic dietary inputs and deploying these targeted physical interventions, we can clear toxic lipid depots and restore the cellular machinery necessary to maintain metabolic health span.